Hello everyone. So, in today's discussion, we are going to see an application of Mayer-Vietris theorem and a result which is known as Jordan curve theorem. In particular, we are going to prove something more generalized than Jordan curve theorem. So, let me just recall what Jordan curve theorem is, and then I will go into the proof and the discussion about that. So, the classical Jordan curve theorem tells you the following thing. Suppose I have a continuous map f from close 0 1 to R2 such that except the boundary f is injective, okay. In particular f is an embedding, okay. So, I will explain what embedding is, okay, such that f is an embedding. Right. So, if it is an embedding, meaning that it is a continuous on the image, it is a homeomorphism, okay. It is a homeomorphism thing. Okay. Its image is in the homeomorphism, that is all. It is continuous injection and all those things. Okay. So, f is an embedding, okay, and f0 equal to f1, f0 to f1, okay. So, let me write it like this. So, rather than write this, let me write down circle to R2. Okay. So, f is an embedding of a circle in R2. So, let us say this is a picture, it is an injective map. So, it does not intersect itself, however, it can does crazy stuff. Okay. So, let us say this is your Jordan curve. Okay. So, such curves are called Jordan curves. Okay. And the classical Jordan separation theorem tells you if I have such a curve and if I look at the complement of the curve in R2, then that consists of exactly two components. So, one will be the interior and another will be the exterior. So, it will consist of exactly two components, two connected components. And you need this theorem to prove many results. For example, Cauchy integral theorem, sometimes you need this result, and also there are versions of for example, Green's theorem, you need this kind of results, where whenever you have a closed curve, these kind of closed curves are called simple closed curves. Okay. This is a closed curve means it starts and ends at the same point, it's the image of a circle, and simple means it does not have an intersection, so it is an embedding. So, once you have a simple closed curve, its complement in R2 consists of only two connected components. Okay. Right. So, what we are going to prove today is a stronger version of that. What we are going to prove is that if I have any embedding of a sphere, any dimensional sphere in Rn, in Sn in Rn, okay, then we will have actually a separation, we will have two components. In particular, we are going to prove that the H0, the zeroth homology is actually z direct sum z if it is. The reduced zeroth homology is isomorphic to Z, which means that it has two connected components. Okay. Right. So, before going into that, let me just first define what is an embedding. So, an embedding f from x to y is a continuous map such that on the image it is a homeomorphism. Okay. So, for example, this is an embedding of a circle onto R2, okay. Right. So, an embedding is simply a map which is a homeomorphism when I restrict it to the image, that is the point here. Okay. It is almost a homeomorphism, but sometimes rather than, so this if you look at this image of a circle, it is just the red curve, rest of the R2 is not touched. So, I have to restrict it to an image, it is a map from S1 to R2 well, but I have to restrict it to an image to get a homeomorphism, that is all. That is a embedding. Embedding basically means you think of the entire thing sitting inside another space without any change. Okay. So, remember one notation. So, by dk we mean the k dimensional closed ball, closed unit ball if you like. Okay. So, first we are going to prove this small lemma which says that if I have an embedding of d of k, okay, if I have an embedding of d of k which is the k dimensional closed ball inside an n dimensional sphere, then the complement of the disk, no matter how you embed, are always going to have trivial homology. And now we are going to focus only on reduced homology. So, this is, let me be very specific, this is for reduced homology. This is, everything is reduced homology. I just want to mention it because this is quite important actually. This is reduced homology. Okay. So, in particular I am going to use the augmentation complex, augmentation map and all those things in the chain complex. Okay. So, on the, if I have any disk, any k dimensional disk inside a n dimensional sphere, its complement is always going to have 0th homology on all level. All the reduced homology is going to be 0. In particular, on the 0th homology, it is going to be connected, okay, and everything else it is going to be 0. So, the complements, the way, another way of saying this is the complement of an embedded disk in Sn is acyclic. Okay. The complement of an embedded disk in Sn is acyclic. Okay. So, this is the first part of the lemma. Using this first part, actually we do not need to use this first part, but anyway, no, we need to use this first part, yeah. So, using this first part, we are going to prove the second result, which is much more important to us, which is the one that we try to prove, is that if my k is less than n, if I have a small dimensional space into a bigger dimensional space, then you have two options. Firstly, if I equal to n minus k minus 1, then it is isomorphic to z. Everywhere else it is 0. What is the meaning of that? Let me just briefly explain what is the meaning of that. So, what I am going to think of Sn as one point compactification of Rn. Okay. So, you remember that with the projection, with the stereographic projection, Sn, you can send Sn to Rn, homotopy equivalent to Rn. Okay. So, in particular, I can replace Sn with Rn, Sn minus 1 point with Rn just by homotopy equivalence via the stereographic projection. Okay. So, the other way around I can think of also. So, Sn I am going to think of as a 1 point compactification of Rn. Okay. And the result says that if I have a smaller dimension sphere inside a bigger dimension sphere, the only possibility where I can get a non-zero homology is when this happens. Okay. So, let us see some examples. Okay. So, let us say I have S1. Okay. S1 is just 2 points. Okay. And let us say I have S1 is circle S0. Let us say S0. Okay. So, let us say k equal to 0. So, what happens there? So, let us say S0, that is just plus minus 1. Okay. And S1 is the circle. Okay. So, if we remove this plus minus 1 from the circle, the complement consists of two disks. This is one, two arcs. This is one and this is one. Okay. Each of them are contractible. Okay. So, only on the ith homology, on the 0th homology, they will give you H0 tilde to be Z. Okay. So, what is 0 here? So, this is n. So, k equal to 0, n equal to 1. So, if I take n minus k minus 1, which is 0, that is the only homology where I am going to get Z, everything else is 0. Okay. Let us go to another example. Let us go to spheres. So, if I look at a sphere, let's look at a sphere. So, I have a sphere. Okay. And inside the sphere, let us say I have the circle S1. Okay. Now, if I remove 2 points from the sphere, what is going to happen? So, first of all, if I remove 2 points from the sphere, I am still going to get connected objects. Okay. So, here what is let me put it in this way. So, if it is yeah, so let's say yeah, so let's say I am having S1 here, that is sitting inside S2. Okay. and if I remember, if I take S2 minus S1, the complement, it is just upper hemisphere and lower hemisphere, both of them are contractible, okay, right. So, if I look at the complement of S2, S1 inside S2, I get two contractible spaces which are connected. So, on the zeroth homology level, the reduced homology level, it will be isomorphic to Z, everything else will be 0, okay. So, if I look at 2 minus 1, that is the 0, there I will get Z, everything else is 0, okay, right. And so, similarly, you can compute this thing, you can check this discussion, that whenever I have a small dimensional sphere inside a bigger dimensional sphere, on the 0th reduced homology, on the only in this case, only in this part, I am going to get 0, everything else is just basically everything else is 0, okay. Now, this is going to be isomorphic to Z, everything else is 0, okay. So, now you can try with some other examples also. S2 minus 1 point you can try. So, see, remember S2 minus 1 point is contractible, it is a point, okay. So, S2 minus 2 point is going to be circle, okay, which has first homology H0, everything else is 0, okay. So, that's okay, yeah, that's another example. Let me just write it down. So, if I look at S2 minus S0, that will be S2 minus plus minus 1, that is just homeomorphic to a circle, okay, right. So, if I take 2 minus 0 minus 1, that is 1. So, on the first homology I am going to get isomorphic to Z, everything else is going to be 0, that is exactly the homology of SO, okay. So, how do we prove such a result? So, this proof is, it is actually based on two simple ideas, simple but very powerful ideas. So, first of all, we are going to prove the complement of a disk inside a sphere, no matter what the dimension is, it has trivial homology in all levels. That is the first thing that I want to prove, that the complement of a disk inside a sphere, complement of an embedded disk inside a sphere has all reduced homology 0, okay. How do we prove such a result? So, this proof consists of two parts. First part, we are going to use the Mayer-Vietoris sequence to show that if I look at the complement of my disk inside a sphere, I can split it into two parts, and homology of each of these parts is going to tell me what is the homology of the entire complement, okay. Let me repeat, I am going to split the complement into two parts, and I am going to show that the entire complement is actually determined by the homology of the entire complement is determined by the homology of these two components, okay. And the next step will be to use our idea of topology of the structures of Sn and Dn to claim that each of these two parts actually have trivial homology, okay. So, let us start with the proof. So, what we want to prove? We want to prove that, remember, this is what we are going to prove first. So, complement of an embedded disk inside Sn has trivial reduced homology on all the levels, okay. So, let us start with an embedding H from a k dimensional disk, closed disk, to an n dimensional sphere, okay. And our goal will be to prove this result using induction, okay. So, let me write it here. So, H is a map, I need a bit more space. So, H is a map from closed disk to Sn, and we are going to use induction on this k, okay, right. So, if k is a 0, if my k is 0, then 0 dimensional disk is just a point, okay. Without convention, 0 dimensional disk is just a point, right. Now, if I look at Sn and I remove a point starting from S1 and all those things, all I am going to get is Rn, okay, everywhere. And this is the point I am looking at reduced homology, because if I start with S0 and if I remove one point, I am still left with one point, okay. So, that is why I am using reduced homology. So, now if I excuse me, if I remove a point from Sn, no matter what the dimension of n is, I am going to get Rn, okay. It is homeomorphic to Rn, Sn minus a point is homeomorphic to Rn. which is cyclic, okay. In particular whose all homologies are trivial, all reduced homologies are trivial. Okay. So, therefore, if k equal to 0, this result is true because Rn is cyclic. Okay. Right. So, we want to prove the complement of a disk inside a sphere is cyclic, always cyclic, and Rn is always cyclic. So, if D is just a point, complement of the point on a sphere is actually homeomorphic to Rn, which is cyclic. So, I am done. Now, I want to prove it induction say. Okay. So, in particular I claim that if I fix a k, any k minus embedding of a k minus 1 dimensional sphere inside Sn has trivial homology, trivial reduced homology, is acyclic. Okay. So, we have assumed that up to k minus 1 we have proved that, that means for any k minus 1 dimensional disk embedded inside Sn, the complement is acyclic. Now, I want to show that complement of a d dimensional disk inside Sn is acyclic. Okay. One of the tricks, the first trick that we are going to do is we are going to replace closed disk by closed boxes. These two are homeomorphic, so I do not have any problem. If I can prove it for closed disk, it will be true for a homeomorphic copy of it. Okay. So, replace dk by ik, and we know that this homology and all this machinery is an invariant under homology homeomorphism. So, the result will still be true. So, the first step is to replace d dimensional closed ball with k dimensional closed ball with k dimensional cubes. Okay. The first step is to replace this one dk with ik. So, what is ik? Ik simply means the k times product of the interval closed interval 0 1, and I can do that because the closed unit disk is closed unit ball is homeomorphic to this object I to the power k, and therefore, in our computation nothing else matters because up to homeomorphism all these machineries are same, up to homeomorphism all these machineries are same. Okay. So, I am going to replace dk with ik, and I am going to prove the complement of k times product of closed unit ball or the closed box is actually acyclic. Okay. So, now what I am going to do is I am going to look at the complement of ik inside Sn. So, my point of interest, my object of interest is Sn minus an embedding of ik, okay. And I am going to write it as a union of two objects A and B, okay. And I am going to use Mayer-Vietory sequence, that is my goal, okay, primarily. So, this is my this is my goal, okay. So, I am defining A to be Sn minus embedding of k minus 1 dimensional cube multiplied by 0 half. So, I go up to half and I lift and remove everything, okay. That is my A, and the other half from half to 1 the complement I am calling B. Okay. So, from Sn I am removing ik minus 1 with first half, and that I am calling A, and I am calling B to be Sn minus I to the power k minus 1 the other half. Okay. So, therefore, because I am talking about the complement, their intersection is Sn minus entire embedding of ik, okay. And their union is just the middle line ik minus 1 cross half, just the middle line, 0 to half, half to 1. So, the intersection is half, okay. The middle line. Remember, we are talking about complement, that is why this intersection is becoming the entire space and the union is becoming only the complement of the half patch, okay. So, now, now I can use the induction. I know that I have, if I remove from Sn an embedding of k minus 1 dimensional sphere. So, ik minus 1 cross half is homeomorphic to ik minus 1. So, therefore, if I am removing the embedding of an ik minus 1 from sphere, n dimensional sphere, by induction we know that it has a trivial homology, trivial reduced homology on all level, in particular it is cyclic. So, therefore, H tilde of A union B is 0 for all I, okay. This is a reduced homology, remember. So, I can use the Mayer-Vietory sequence, the reduced version of Mayer-Vietory sequence, and we get the following. So, H I plus 1 tilde of A union B, that is 0, A union B by induction cyclic. goes to hi tilde of A intersection B. That is our subject of interest. So, remember A intersection B is complement of k dimensional embedding of k dimensional cube in Sn. That is my interest, A intersection B. That goes up to hi tilde A, direct sum hi tilde B, that goes to hi tilde A union B, that again is cyclic. So, this is 0, this is 0, mere vector is an exact sequence. So, in particular this is an isomorphism. Okay. So, therefore, because it is an exact sequence, I have an isomorphism between hi tilde of A intersection B from go to hi tilde A and hi tilde B. Now, recall slightly what was this phi map in mere vector sequence. On the chain level, if I have alpha which was A intersection B, then this map phi of alpha which induces capital phi actually goes like this, I hash alpha comma minus of j hash alpha. So, the intersection goes inside both A intersection B goes inside A and B. Okay. Call this inclusions as I and J. Okay. And so, the first component I am just putting the cycle inside itself from A intersection B to A. The second component from A intersection A to B I am just putting it with a negative sign. Okay. So, apart from sign, apart from the sign of the objects, these are just embedding, they are just inclusion map, the cycles are simply getting inclusion. So, the phi is induced by the inclusion map. Okay. Remember that. Okay. So, because up to sign phi is induced by the inclusion in the chain level, what will happen is I can use this map to understand the homology of this one. Okay. So, all I have to compute now is the homology of this one, which is same as homology of this one. So, all I have to compute now is the homology of these two. Okay. Now, suppose I have, so now I want to prove that this is 0. So, all I have to show is these things are 0, okay, that is the point. Okay. Now let us say suppose alpha is an element, it is a chain which is non-zero on the ith homology of Sn minus Ik, which is here. That means its image, because its inclusion, its image as a homology group will either be non-zero here or it will be non-zero here. That is the first thing. Okay. In particular, if I am thinking of this as a cycle, then this chain as a cycle here, it is a non-trivial cycle, so it is not a boundary of anything. So, it will not be either a boundary here or a boundary here. If it is boundary on both of them, then it has to be 0, that means alpha will be 0. Okay. So, it will either be not a boundary here or not will be a boundary here. One of these two has to happen. So, in particular, if this cycle alpha is non-zero, non-homologous to 0 in here on the left hand side, it must be non-zero in one of them. In particular, alpha is not a boundary in at least one of A and B. And this is the entire part of the proof or the argument, is to make sure if I want to show that this thing has a trivial homology, I can prove it using the proof that these two has trivial homology, and if something is non-trivial here in the homology, it must be non-trivial here in one of them, one of these homologies. Okay. One of these homologies. Now, the point here is you can notice that when I am going from here to these two, I am actually splitting this last part. Okay. So, from Hik minus 1 cross I, here I am going I by 2, here I am going I by 2, the length is small, first up, second up. Now, alpha is a cycle which is non-trivial here, so alpha must be non-trivial either here or here, it is not a boundary either here or here. Now, what I am going to do is, I am going to make the process repeat again. Okay. What will happen? Okay, let us say alpha is not a boundary here. Use the process again and split this further into two parts, 0 1 by 4, 1 by 4 half. Same argument will tell you that alpha will not be a boundary in one of those two also. Repeat the process again. If you keep on repeating, you are splitting the interval by half, 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 half. So, on the limiting part, on the limit, you are going to left only with a number, okay, because you are making it smaller, 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 smaller. On the limit, you are going to lift up with a number. And so, on the limiting sense, these component will converge to ik minus 1 some point, which is just ik minus 1. And by induction, everything on the complement of ik minus 1 has a 0 homology. So, that cycle must be a boundary there, and from there using compactness you have to somehow claim that alpha is also must be a boundary in either one of them. Okay. So, let us dive into the proof. There is a slight trick involved, there is a slight technicality involved that I want to mention here, which is very crucial, which is particularly very, very crucial. So, start with an element, assuming that the homology is non-zero, there is a non-homologous, non-zero homologous element, call it alpha, that is a cycle which is not a boundary. So, it must not be a boundary in either this one or this one. Okay. So, without loss of generality, suppose this is let's say without loss of generality, it is not a boundary in one of them. Suppose that alpha is not a boundary, suppose alpha is not a boundary in the first component A, okay, which is Sn minus h ik minus 1 cross 0 half. I do the same thing again. So, A is now my object of interest, okay, right. Again I split it into two parts, call it A11, A12, let us say. One part 0 to 1 by 4 and the second part, so again split it into two parts. One part will be A11, let us call it A11, which will be Sn minus h of ik minus 1 cross 014, A12 which is Sn minus h ik minus 1 cross 14 half. Okay. So, now I use the same argument, alpha is not boundary on here. So, alpha must not be in boundary, again the mere variator I can apply, or I can directly write down everything else. I can use the same thing in the intersection, it will look like ik minus 1, induction will tell you that it is trivial. So, mere variator tells you that alpha is either not a boundary here or not a boundary here. So, let us say it is not a boundary here, okay. I apply the logic again. Okay. So, starting from this interval I call this I1, this let us say here it is non-trivial, I call it I2, I keep on splitting the interval 0, 1 into smaller and smaller pieces. So, we iterate the process above to consider a nested sequence of closed interval I1 which contains I2, which contains I3 and so on and so forth, and these are, so you are taking the interval, you are splitting into half, again splitting into half, again splitting into half. So, finally, you are going to converge to a point. Okay. So, if I just keep on splitting into half all those things. So, if I focus on one particular interval, it is getting smaller, 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 it converges to a some point. Okay. Right. So, therefore, I can write ik as ik minus 1 cross ij. Okay. So, what happens if I look at this nested sequence, ik minus 1 I1, ik minus 1 I2, ik minus 1 I3, alpha is not a boundary of them, of alpha is not a boundary in Sn minus h of ik minus 1 into ij for all j. Okay. The same argument, so let me write it, the same argument, alpha will not be a boundary of a chain in Sn minus h I k minus 1 into ij for every j. This is true. Okay. But what happens here is that if I go to limit, if I go j tends to infinity, that I am splitting again, I am getting to a point P, okay, and that point here the object looks like ik minus 1 cross P, which is just k minus 1 dimensional object. Okay. And here I know that every reduced homology is trivial, it is acyclic. This is by induction assumption. So, this is induction step. Induction assumption. Okay. So, by induction, alpha is a boundary of a chain, say beta, in here. Okay. Now, here there is a small technical point. First of all, alpha is a cycle and alpha is a boundary of chain beta in here. Right. Now, because beta is a finite linear combination of simplices, it must be compact. Now, this thing is crucial. Actually, what I am assuming is here actually I may have to change it a little bit because beta might not be a simplicial compact. So, beta in this case I am just assuming beta to be a boundary element. Okay. So, it is a finite linear combination of simplices and its image. So, boundary is an image of something, alright, and delta is a boundary map which takes n simplices to n minus 1 simplices. Okay. So, therefore, this beta is a finite linear combination of simplices and this is compact. Okay. Now, what happens to this compact set beta? Beta is in here, that means beta is in the intersection of all of these, actual union of all of these objects. So, this one is, so let me write it down. So, beta, so this Sn minus h of I k minus 1 cross p, this is nothing but Sn. So, let me write it in terms of union. So, everything is happening in the complement. So, this is union of union over j Sn minus h of I k minus 1 cross I j. Okay. Right. And these are nested sequence of open sets. This is a point that you have to understand, is that these sequences I1 is contained in I2 is contained in I3. So, this is getting smaller and smaller and smaller. You are looking at a complement. So, they are getting bigger and bigger and bigger, and their entire union contains this one. Okay. So, this is an open cover of this set. In particular, beta is a compact subset of here. Beta belongs to here, it is a compact set which is covered by union of these objects. Okay. So, by compactness, beta is union of finitely many of them actually. Okay. And now, because they are nested, one is containing another, it is containing another, it is containing another, this is an increasing sequence. Because it is contained in finitely many of them, it must be contained in one of them, which is the biggest one in that chain. Okay. So, this ij is decreasing in the length. So, the complement is increasing, and so beta is contained finitely many of them, take the highest one. Okay. So, all of this argument tells you that beta is a chain in one of these. However, our claim was that beta is a chain, okay, in one of them. That means in that chain alpha is actually boundary of beta, because beta is lying there. Alpha is a boundary of beta, already we know inside them, and it is sitting inside one of the simplices. So, alpha must be a boundary of the chain beta, okay, which tells you that alpha is 0, alpha is homologous to 0 element, because if something is a boundary, some cycle is a boundary, then it is trivial in homology. Okay. So, therefore, by our assumption, alpha must be a boundary of this chain in here, of chain in here. And this is a contradiction to our assumption, because we have assumed that each iterated step is alpha is not in the boundary of either of this component, and now we have obtained that in one of this component alpha is actually boundary. Therefore, alpha must be 0. Okay. Therefore, our assumption is not true. So, therefore, every element of a reduced homology of the complement of of a disk in Sn has to be trivial. In particular, complement of an embedded disk in Sn has trivial homology, is cyclic. So, what do we prove? So, we prove the first part, which is saying that the complement of a closed disk inside Sn has trivial homology, trivial reduced homology on all level, in particular is acyclic. Okay. So, we have replaced dk by ik and everything else is same. Now, we want to prove what is called the Brouwer, generalized Brouwer's theorem, which says that if I have a smaller dimension sphere on a bigger dimension sphere embedded, then the reduced homology is completely determined by these two factors, namely it will be isomorphic to Z if I equal to n minus k minus 1 and it will be 0 if I is not equal to n minus k minus 1. In particular, if I put k equal to n minus 1, okay. So, if I look at let's say I put k equal to n minus 1. Okay. So, what will happen in this side? It will become n minus 1 minus 1, that will be 0. Okay, that will be 0. So, therefore, if I remove an n dimensional embedded n minus 1 dimensional embedded sphere from an n dimensional sphere, the complement will have cyclic, will be cyclic. That means only on the 0th level you will have the reduced homology Z that will be connected. Everywhere else, that will be only two component, everywhere else it will be 0. Okay. Now, what we are not saying that the complement will be contractible. All you are saying is the complements are actually 0 homology on higher dimensional level. Okay. We are not claiming that the complements are contractible. Although part of it is actually true, in dimension true, it actually indeed happens. Okay. So, now let us go to this proof of how we can show. Now, the first, how do you go from here to there? So, let me just mention how do you go from here to here. Remember that Sn can be written as a union of two disks which are upper hemisphere and lower hemisphere, and the intersection is Sn minus 1. Okay. So, now we are going to use that decomposition and the mere variatory sequence there, and then I am going to use this previous lemma to claim out this one. Okay. So, let us go to the part of proof B. Okay. So, we will proceed by induction on K. So, what do I have to prove? I have to show that Hi tilde of Sn minus H of Sk is isomorphic to two part. It is 0 if I equal to n minus k minus 1 and it is 0 otherwise. Okay. So, first we are going to prove it using induction. Okay. So, essentially what we are going to prove is this thing is homotopy equivalent to S of n minus k minus 1. Okay. And then the homology of S of k n minus 1. So, this is, so if you look at this is nothing but, homology of S of n minus k minus 1. Okay. That is the reduced homology. It is 0 on exactly on the dot of the dimension, everywhere else it is 0. Isomorphic to Z on the dot of the dimension, everywhere else it is 0. Hn of Sn is isomorphic to Z, Hn tilde of Sn, Hn tilde of Sn is isomorphic to Z, everywhere else it is 0. Okay. So, we are going to proceed by induction. So, first assume that k equal to 0. Okay. So, S0 is just 2 point. Okay. So, because S0 is just 2 point, Sn minus 2 point is isomorphic to Sn minus 1 cross R. Okay. Right. Sn minus 1 cross R, and so therefore, it is homeomorphic up to Sn minus 1 cross R. Okay. So, then how do we prove that the you can check this, that this part I have not done, but you can check this, that this thing, this object Sn minus 1 minus R, this is homotopy equivalent to Sn minus 1. Okay. And therefore, so basically what I am saying is something cross R, and R is homotopic to a point. So, this is homotopic equivalent to a point cross Sn minus 1. So, check that Sn cross R is homotopy equivalent to Sn minus 1. Okay. Therefore, this has the same homology as homology of Sn minus 1, which is what I have written here, k equal to 0 in this case, and therefore, our assumption is true. Okay. Now, in the induction step, write Sk as 2 hemisphere dk plus dk minus. Okay. So, in circle you have, let me draw that. So, in circle you have so this is this hemisphere and this hemisphere, okay, and the intersection is S0 on S2. Let us just say that one side we have this hemisphere, other side we have this hemisphere, and intersection is S1. And so, this we can do in general. Actually, you can take Sn minus Sn and then you remove the north pole and remove the south pole, and their complement will be homeomorphic to the disk, and their intersection will be Skn minus 1. Okay. So, I write Sn as union of upper hemisphere and lower hemisphere whose intersection is Sn minus 1. Okay. So, then I can take A to be the complement of this disk in Sn and B to be complement of this disk in Sn, and I can use part 1, part A, where I know that these are acyclic. They are simply acyclic. Okay. So, this one has all trivial, this one has all trivial. Now, I can use the Mayer-Vietory sequence again. Okay. Mayer-Vietory sequence tells me the same earlier case, that Hi tilde of A intersection B, which is isomorphic to Hi tilde of A direct sum Hi tilde of B. Okay. So, now what do we have here? We have that sorry, this is trivial. Sorry, so this is trivial. No, this is not true. This is trivial. So, let me write it down. So, this is what does that Mayer-Vietory sequence tells us. So, Mayer-Vietory sequence will tell me that Hi A intersection B goes to Hi of A direct sum Hi of B goes to Hi of A union B goes to Hi minus 1 of A intersection B, and so on and so forth. Okay. Now, so let me write it. This is Hi plus 1 A union B. Okay. Right. And here I have written the wrong part of the sequence. So, let me write down the correct part of the sequence. I have Hi of A union B here, and then I have Hi minus 1 of A intersection B. This is Hi minus 1 A direct sum Hi minus 1 B, and here you will have Hi A direct sum Hi B. Okay. Now, this is 0, this is 0. So, the Mayer-Vietory sequence tells us that this is an isomorphism. Hi of A intersection B is isomorphic to Hi minus 1 of A intersection B. So, what is A intersection B? So, the A intersection B is simply H of, so this is A union B is Hi minus 1 of A intersection B. So, A union B is basically this one, Hi of Sn minus Hi of Sk minus 1, and A intersection B is Hi of Sn minus Hsk. Okay. So, Mayer-Vietoris tells me that these two are isomorphic. So, what is happening here? I is going to I plus 1, k is reducing to k minus 1. Okay. Now, in the induction step, we have assumed that this object has homology isomorphic to Z whenever this I plus 1 is n minus k minus 1. Everywhere else it is 0. In particular, here if I put plus 1 here extra and I get minus 1 extra, this summation is not changing. Okay. So, therefore, I can just keep on using induction at each stage, and I can reach to a stage where I realize that okay, if I is equal to n minus k minus 1, in this, so for example, next step itself here, if I start with I to be k minus 1, n minus k minus 1, this one will tell me that this is isomorphic to Z. Okay. So, that means here also it will give me n minus k minus 1 will be isomorphic to Z. Okay. If it is 0, everywhere else it is 0. Okay. So, only on the 0th, so just the easiest way of understanding this thing, focus on what is n minus k minus 1. Okay. When I equal to n minus k minus 1, only on that stage this is giving me isomorphism from the lower dimensional assumption, from the induction assumption. Everywhere else it is giving me 0. Okay. So, via induction we have proved that this thing is true. Okay. Our assumption is true. Okay. So, let me give you the conclusion, which is the Jordan separation theorem. Let me write down this as a corollary of Jordan separation theorem. Jordan separation theorem, which says that if I have an embedding, let f, so if h from S1 to R2 is an embedding, then R2 minus S1 has two components, two path components. Okay. So, how does this proof work? So, first of all, you think of R2 as homotopy equivalent to S2 minus a point, or S2, R2 is homotopy equivalent to R2 union infinity is homotopy equivalent to S2. Okay. So, I can embed R2, embed R2 inside S2. Okay. So, I have an embedding H1 from S1 to R2, R2 embeds inside S2. So, I get S2 here. Okay. So, proving it has two component in R2 is same as proving two component in S2, and one of the things that in this embedding I have this S2, and so I can think of R2 this as homotopy equivalent to R2 union infinity. Okay. So, in H1 going from S1 to S2, it will in our by our earlier result H0 of S2 minus H of S1. This, if you look at, so this is 2 minus 1 minus 1, so that is isomorphic to Z. Okay. So, therefore, this will imply that this has two components. So, the reduced homology being Z means it has 0th reduced homology being Z means it has two components. So, this S2 minus HS1 has two components, two path components. Okay. In fact, you notice here that one of these path component must contain this infinity. Okay. So, one of this path component will be unbounded. Okay. And so, essentially what we can show is essentially that this components. This has two path component, one of them is unbounded and one of them is bounded. In fact, it is actually true that each of these components are homeomorphic to disk, but that requires a bit more technicality to prove that. In fact, in higher dimension it is partially true also. Okay. So this is one particular case of Jordan separation theorem that we have proved, is that Sn sitting inside a smaller dimension sphere sitting inside a higher dimension sphere essentially behaves like n minus 1 minus k dimensional sphere, okay, up to homology. So it will be isomorphic to Z if I equal to n minus k minus 1, everywhere else it is trivial. Okay. So let me go back to this result again and repeat what I have just said. So the first part of this one says that if I have an embedding of a closed disk inside a sphere, no matter how you are looking at it, if it is embedded inside sphere, its complement is always acyclic, has all trivial homologies, trivial reduced homologies. Okay. So if I am looking at in terms of normal homology, so this in particular says that complement of a disk on a sphere, of a closed disk on the sphere, has two connected components. That is clearly there, the part of this thing, okay, as a two connected components. Okay. Because the 0th level also is sorry, has only one, has only one connected component, because the 0th reduced homology is also 0. Okay. So you can think of it as like if you have a sphere, if you remove a disk, it will have one connected component. If you reduce a point, it will also have one connected component, and so on. Okay. Now the other thing that it says is that if you have an embedding of a k dimensional sphere inside an n dimensional sphere, then except one homology, which is n minus k minus 1, everything else is isomorphic to 0. Okay. So it behaves like n minus k minus 1 dimensional sphere in some sense. Okay. So in particular, if n equal to I equal to n minus k minus 1, in particular if I look at k equal to n, okay, so that is n minus, sorry, k equal to n minus 1. So this is the particular case that I was discussing, that k equal to n minus 1. You will get the 0th reduced homology, that is isomorphic to Z. That means it will have two connected components. So if I remove Sn minus 1 from Sn, I will have two connected components. Okay. So you can reduce these things, and everywhere else if I remove that, the connected component will be 0. So there we will have only one connected component. Okay. Right. So this is one of the thing about complement of a disk and complement of sphere inside a lower dimensional sphere. One of the things that we can kind of consider here also is that in this case you can ask what happens in general if I look at, let us say, high dimensional sphere putting inside a lower dimensional sphere. This does not tell you this has no restriction of k and n. This one has a restriction of k and n, this has no restriction of k and n. So in particular, if I am looking at high dimensional disk embedded inside Sn also, this is the same thing going to be true, although we know from invariance of domain that cannot be possible, we cannot do that. Okay. So this is what is called Jordan separation theorem, and in R2 in particular this says that if I look at an embedded circle inside R2, its component, its complement has two connected components. Okay, so this will be all for this lecture. Thank you.